Imagine waking up one morning to find that every single large animal on Earth had vanished overnight. No elephants trumpeting in the distance, no whales singing in the depths, no lions prowling the savannah. Just silence. Empty ecosystems. A world stripped bare of its giants. That's essentially what happened 66 million years ago, except it wasn't overnight. It was in a matter of hours, minutes even. And it wasn't just the large animals. 3/4 of all life on Earth simply ceased to exist. But here's what makes this story truly haunting. The creatures that died that day had no idea what was coming. They went about their daily routines, hunting, grazing, nesting, completely unaware that hurtling toward them, through the cold vacuum of space, was a mountain of rock and metal, a cosmic bullet that would rewrite the entire story of life on our planet. This wasn't some gradual climate shift that took millennia to unfold. This wasn't a volcanic eruption that gave species time to adapt or migrate. This was instantaneous planetary devastation on a scale so massive that it defies human comprehension. In the time it takes you to blink, the age of dinosaurs ended and the age of mammals began. Today, we're going to walk through that day step by step. Not just the moment of impact, but the chain reaction that followed. The physics, the chemistry, the biology of mass extinction happening in real time. We're going to explore how scientists pieced together this ancient crime scene using clues buried in rock layers around the world. And we're going to discover why this single event, lasting mere moments, shaped the world we live in today. Because without the Chicxulub impact, there would be no flowering meadows, no grasslands stretching to the horizon, no forests filled with birdsong, no primates swinging through jungle canopies, no humans telling stories around campfires. The world would still belong to the dinosaurs, but instead, in one catastrophic moment, evolution hit the reset button and began writing an entirely new chapter. The story begins not on Earth, but in the asteroid belt between Mars and Jupiter. Picture a region of space filled with rocky debris, remnants from the early formation of our solar system. Most of these chunks of rock and metal orbit peacefully, locked in their cosmic dance for millions of years. But sometimes, gravitational forces conspire to nudge one of these objects out of its stable orbit. The object that would eventually become known as the Chicxulub impactor started its journey toward Earth long before dinosaurs ever walked the planet. For millions of years it drifted through the void, a dark wanderer following the invisible pull of gravity. It wasn't particularly large by asteroid standards, perhaps 6 to 10 miles in diameter. You could walk across it in a few hours if it had a solid surface to walk on. But what it lacked in size, it more than made up for in velocity. By the time it entered Earth's atmosphere, this cosmic projectile was traveling at roughly 45,000 miles per hour. To put that in perspective, a rifle bullet travels at about 2,000 miles per hour. The space shuttle reached speeds of 17,000 miles per hour. This asteroid was moving more than twice as fast as the fastest human-made object, and it carried the kinetic energy of billions of atomic bombs. But the dinosaurs living in what would one day become Mexico had no concept of asteroids or space or kinetic energy. They lived in a world that was already ancient beyond imagination, yet still young compared to Earth's full history. The global temperatures were warmer than today. Late Cretaceous period was a time of abundance. Sea levels were higher. There were no ice caps at the poles, no frozen wastelands, just steaming with life. Endless tropical and subtropical landscapes. Dinosaurs wandered through lush forests, their calls. Massive herds of duck, biled echoing across primeval valleys on ferns and cycads, their club. Armored ankylosaurs, browse-tails swaying as they moved. In the rivers and coastal waters, enormous crocodilians basked in the sun, while marine reptiles like mosasaurs and plesiosaurs ruled the seas. Flying reptiles with wingspans larger than small airplanes soared overhead. And then there were the Tyrannosaurs, apex predators that had perfected the art of killing over millions of years of evolution. Their massive skulls housed brains sophisticated enough to coordinate pack hunts. Their powerful legs could carry them at speeds approaching 25 miles per hour, and their bone-crushing jaws could generate bite forces of over 12,000 pounds per square inch. They were the ultimate predators in an ecosystem that had been stable for millions of years. None of them saw it coming. The first sign would have been a brilliant streak of light across the sky, brighter than the sun. As the asteroid tore through Earth's atmosphere, friction heated its surface to temperatures exceeding those found in the core of stars. The air itself began to glow. For a few seconds, any creature looking up would have seen what appeared to be a second sun racing across the heavens. But those few seconds were all the warning they got. The asteroid struck the shallow sea off the coast of the Yucatan Peninsula with the force of 10 billion Hiroshima bombs. The impact created a crater over 100 miles wide and 12 miles deep. To put that in perspective, if you stood at the center of this crater, the rim would be beyond the horizon in every direction. The energy released was so immense that it instantly vaporized both the asteroid and millions of tons of rock from the impact site. The first effect was the shock wave. Traveling faster than sound, it radiated outward from ground zero like an invisible wall of destruction. Trees were ripped from their roots and flung through the air like twigs. Mountains crumbled. The very crust of the earth buckled and heaved like a stormy sea. Any dinosaur within several hundred miles of the impact site was killed instantly, not by heat or debris, but by the shockwave itself. Their internal organs liquefied from the sudden change in pressure. It was over before their nervous systems could even register what was happening. But the shockwave was just the beginning. The impact ejected trillions of tons of molten rock and debris into the atmosphere. Some of this material was blasted so high that it actually escaped Earth's gravitational pull entirely, scattering into space. But most of it followed ballistic trajectories, arcing high above the planet before raining back down as a global shower of superheated glass and rock. This is where the story becomes truly apocalyptic. As this debris re-entered Earth's atmosphere all around the globe, friction heated it to incandescent temperatures. The sky began to glow red hot. The air itself became an oven. Any organic material exposed to this radiant heat burst into flames spontaneously. Forests that had stood for millions of years ignited simultaneously across entire continents. The Amazon rainforest of the Cretaceous became a continental wildfire in a matter of minutes. Dinosaurs that had survived the initial shockwave now faced a new horror. Their world was literally on fire, but even this wasn't the end of the immediate effects. The impact had thrown so much debris into the upper atmosphere that sunlight began to dim. What started as a bright, clear day gradually darkened as particles of dust and soot spread across the sky. Within hours, a perpetual twilight had descended over the entire planet. This was the beginning of what scientists call impact winter. Just as volcanic ash can cool global temperatures by blocking sunlight, the debris from Chicxulub created a planet-wide shroud that would persist for months or even years. Temperatures plummeted. Photosynthesis slowed, then stopped entirely in many regions. The base of the food chain began to collapse. Plants that had never experienced prolonged darkness began to die. Without plants, herbivorous dinosaurs had nothing to eat. Without herbivores, carnivorous dinosaurs faced starvation. The intricate web of relationships that had sustained Cretaceous ecosystems for millions of years unraveled in a matter of weeks. But the impact winter was only one part of the crisis. The asteroid had struck a region rich in sulfur-bearing rocks, and the impact vaporized these deposits, sending sulfur dioxide high into the atmosphere. When this gas mixed with water vapor, it formed sulfuric acid droplets that began falling as acid rain. This wasn't the mild acid rain we worry about today from industrial pollution. This was concentrated sulfuric acid falling from the sky in quantities that could strip leaves from trees and burn the skin of any animal caught in the open. Rivers and lakes became too acidic to support life. The ocean's chemistry shifted dramatically as acid rain poured into the seas. Marine ecosystems, which had seemed safely insulated from the terrestrial catastrophe, now faced their own crisis. The microscopic plankton that formed the base of ocean food webs began dying en masse. Coral reefs dissolved in the acidified water. Fish populations crashed. The great marine reptiles that had ruled the seas found themselves in a world as hostile as the burning continents. And still, the cascade of destruction continued. The impact had triggered earthquakes that registered off any scale we use today. These seismic waves traveled around the entire planet, triggering landslides, volcanic eruptions, and massive tsunamis. Along coastlines thousands of miles from the impact site, waves hundreds of feet high crashed ashore, carrying marine sediments far inland and leaving behind geological signatures that scientists can still read today. Some researchers believe the impact may have been powerful enough to trigger volcanic activity on the opposite side of the planet. In what is now India, massive volcanic eruptions were already underway, creating the geological formation we now call the Deccan Traps. The timing suggests these eruptions may have intensified in response to seismic waves from the Chicxulub impact, adding even more ash and toxic gases to an already poisoned atmosphere. Within days, the planet had transformed from a lush, warm greenhouse world into a cold, dark, toxic wasteland. The air was unbreathable, the water was poisonous, the land was buried under ash and debris. For the first time in hundreds of millions of years, Earth resembled the hostile, lifeless world it had been in its earliest days. Yet somehow, some creatures survived. In burrows deep underground, small mammals rode out the firestorm and the impact winter. Their modest energy requirements and ability to hibernate helped them survive when larger animals could not. In the depths of the ocean, some fish and marine invertebrates found refuge from the acid rain and temperature swings. Seeds buried in soil waited patiently for conditions to improve. But for the dinosaurs, the rulers of Earth for over 160 million years, this was the end. The few that survived the initial catastrophe faced a world that could no longer support them. Without plants to eat, without stable temperatures, without clean air and water, even the mightiest tyrannosaur was helpless. The age of dinosaurs was over. The age of mammals was about to begin. But the story doesn't end with the extinction. In fact, in many ways it's just beginning. Because what happened in the months and years following the impact is just as remarkable as the catastrophe itself. This is the story of how life found a way back from the brink of total annihilation. Picture Earth 6 months after the impact. The fires have finally burned out, leaving behind a landscape of charcoal and ash. The debris in the atmosphere has begun to settle, allowing weak sunlight to filter through for the first time since the impact. But this isn't the vibrant green world that existed before. This is a planet in black and white, a monochrome wasteland where the only sounds are wind whistling through dead trees and the occasional splash of acid rain. The temperature has dropped by as much as 20 degrees Fahrenheit globally. What were once tropical paradises are now frozen wastelands. The few survivors huddle in whatever shelter they can find, burning through their body fat reserves just to stay alive. Most will not make it through the first winter, but life, as it always does, finds the most unexpected ways to persist. In the darkness beneath the soil, fungal networks that had been quietly decomposing organic matter for millions of years suddenly found themselves in paradise. The global wildfires had created the largest feast of dead plant material in Earth's history. While other organisms starved in the perpetual twilight, fungi thrived, spreading their thread like hyphae through the ash-covered ground. These fungal forests became the foundation of the post-impact world. They broke down the massive deposits of dead organic matter, releasing nutrients back into the soil. They created the chemical conditions necessary for new plant growth when the light finally returned. In a very real sense, fungi saved the world by cleaning up the mess left by the asteroid. Meanwhile, in freshwater lakes and streams that had somehow avoided the worst of the acid rain, small fish populations began the slow process of recovery. These weren't the massive marine reptiles that had dominated Cretaceous seas. These were humble creatures, often no larger than your hand, that had survived by being inconspicuous and adaptable. But perhaps the most important survivors were the ones we rarely think about, the microscopic organisms that form the invisible foundation of all life on Earth. Bacteria and algae that had been dormant in lake sediments began to multiply as conditions slowly improved. These tiny organisms would be the first to restart the process of photosynthesis, gradually removing carbon dioxide from the atmosphere and replenishing oxygen levels. The recovery wasn't uniform across the planet. Some regions, particularly those that had been hit hardest by the initial impact effects, remained barren for thousands of years. But in other areas, especially those with abundant freshwater sources and some protection from the worst of the acid rain, life began to reassert itself with surprising speed. The first plants to return weren't the towering trees or lush ferns of the Cretaceous. They were simple, hardy species that could tolerate poor soil conditions and low light levels. Mosses crept across the ash-covered ground. Small flowering plants pushed through the debris. Grasses, which had been relatively uncommon during the age of dinosaurs, suddenly found themselves with unlimited room to spread. These pioneering plant communities created opportunities for the animal survivors. Small mammals emerged from their burrows to find a world transformed. Without large dinosaurian predators to worry about, they could explore territories that had been off-limits for millions of years. They diversified rapidly, evolving into ecological niches that had never existed before. Some became specialized seed eaters, taking advantage of the abundance of grass and small flowering plants. Others developed strong digging claws and began hunting for insects and grubs in the rich organic soil. A few took to the water, becoming the ancestors of early whales and dolphins. The evolutionary explosion that followed the extinction was as dramatic as the extinction itself. But the most remarkable recovery story belongs to the birds. These dinosaur descendants had survived the impact by virtue of their small size, their ability to fly to new food sources, and their relatively low energy requirements. In the post-impact world, they found themselves the sole inheritors of their dinosaurian legacy. Without competition from their larger relatives, birds rapidly diversified into forms we can barely imagine today. Some grew to enormous sizes, becoming the apex predators of the early Paleocene. Others specialized for specific diets or habitats, filling ecological roles that had been vacant since the extinction. The recovery process took millions of years, but it was surprisingly thorough. By 10 million years after the impact, Earth's biodiversity had largely recovered, though it looked nothing like the world that had existed before. Gone were the giant ferns and cycad forests. In their place were grasslands and deciduous forests dominated by flowering plants. Gone were the dinosaur herds that had trampled ancient valleys. In their place were growing populations of mammals, experimenting with forms and lifestyles their ancestors could never have imagined. This transformation reveals one of the most profound truths about life on Earth. Mass extinctions aren't just endings. They're also beginnings. They clear away established ecological relationships and create space for evolutionary innovation. The mammals that inherited the post-Chicxulub world weren't just lucky survivors. They were pioneers in a fundamentally new type of ecosystem. The flowering plants that came to dominate post-extinction forests created opportunities for new types of pollinating insects. These insects, in turn, supported new types of insectivorous mammals and birds. The grasslands that spread across formerly forested continents created niches for grazing animals and the predators that hunted them. But perhaps most importantly for us, the extinction of the dinosaurs created the conditions that would eventually allow primates to evolve. In a world still dominated by giant reptiles, our mammalian ancestors would likely have remained small, nocturnal creatures hiding in the shadows. The impact that ended the Cretaceous didn't just kill the dinosaurs, it opened the evolutionary pathway that would eventually lead to humans. This brings us to one of the most haunting aspects of the Chicxulub story. The event that seemed like the ultimate catastrophe was actually the ultimate creative force in Earth's history. Without that asteroid impact, there would be no humans to contemplate their own existence. No art, no music, no literature, no science. No consciousness capable of looking back across deep time and understanding its own origins. Yet the story of Chicxulub isn't just ancient history. It's a reminder that our planet exists in a cosmic shooting gallery, where impacts from space are not just possible, but inevitable. The asteroid that killed the dinosaurs was not unique. Earth bears the scars of hundreds of impact craters, though most have been erased by geological processes over time. Scientists estimate that an impact capable of causing mass extinction occurs roughly once every 100 million years. The last one was 66 million years ago. Simple mathematics suggests we're overdue, though the random nature of cosmic impacts means the next one could happen tomorrow or not for another 100 million years. This uncertainty has led to one of the most important scientific endeavors of our time, the systematic search for potentially hazardous asteroids. Unlike the dinosaurs, we have the technology to see death coming from space. We can track the orbits of dangerous objects and, theoretically at least, develop methods to deflect them before they reach Earth. But even with our advanced technology, we remain vulnerable in ways the dinosaurs never were. Our interconnected global civilization could collapse from impacts that wouldn't have phased Cretaceous ecosystems. A relatively small asteroid hitting the right target, a major city, or a key piece of infrastructure could trigger cascading failures that might take decades to recover from. The dinosaurs had no choice but to accept their fate when the sky began to glow 66 million years ago. We have the luxury of choice, but only if we choose to use it. The story of Chicxulub is ultimately a story about the fragility and resilience of life itself. It shows us that even the most successful organisms, even the most stable ecosystems, can disappear in an instant when faced with forces beyond their control. But it also shows us that life itself is incredibly persistent. Given enough time, evolution will find a way to fill every available niche, to adapt to every challenge, to recover from every catastrophe. The question for our species is whether we'll be among the survivors or among the casualties when the next great test comes. The Chicxulub impact crater still exists today, buried beneath the Yucatan Peninsula and the Gulf of Mexico. It's invisible from the surface, hidden by millions of years of sediment deposition. But it's still there, a permanent scar on our planet's face, a reminder of the day the world changed forever. Scientists continue to study this ancient crime scene, drilling deep into the crater structure to understand exactly what happened during those crucial hours and days after impact. Each new discovery adds another piece to the puzzle, helping us understand not just how the dinosaurs died, but how we came to exist in their place. The story of the Chicxulub impact is ultimately our story. Every breath we take, every step we make, every thought we think is possible only because of what happened on that terrible day 66 million years ago. We are the children of catastrophe, the descendants of survivors, the inheritors of a world remade by cosmic violence. And somewhere out there in the darkness of space, another asteroid may already be on its way. The scientific detective story of how we discovered the Chicxulub impact reads like the greatest mystery novel ever written. For over a century, paleontologists had puzzled over one of the most perplexing questions in Earth's history. Why did the dinosaurs vanish so suddenly from the fossil record? The evidence was clear that something catastrophic had happened at the end of the Cretaceous period, but the cause remained maddeningly elusive. The first clue came from an unlikely source, a thin layer of clay found in rocks from exactly the right time period. This wasn't just any clay. When scientists analysed its composition in the 1970s, they found something extraordinary. The layer contained concentrations of iridium that were hundreds of times higher than normal levels found in Earth's crust. Iridium is one of the rarest elements on our planet's surface. It sank deep into Earth's core during the planet's formation, leaving only trace amounts in the rocks we can access. But iridium is much more common in asteroids and comets. When Luis and Walter Alvarez first proposed that this iridium spike was evidence of an asteroid impact, the scientific community was skeptical. The idea seemed too dramatic, too catastrophic for a profession that had long believed in gradual change over geological time. But the evidence kept mounting. The iridium layer wasn't found in just one location. It appeared in rocks of the same age all around the world. From Denmark to New Zealand, from Montana to Spain. This thin band of iridium-rich sediment marked the exact moment when 3/4 of all species disappeared from the fossil record. It was like finding the same fingerprint at crime scenes on every continent. Then came the shocked quartz. When rocks are subjected to extreme pressures far beyond anything found in normal geological processes, their crystal structure becomes deformed in distinctive ways. This shocked quartz had only been seen before at nuclear test sites and other known impact craters. Yet here it was, embedded in the same layer as the iridium, scattered across the globe like confetti from a cosmic explosion. The smoking gun came in the 1990s, when scientists finally located the crater itself. Using gravity mapping and magnetic surveys, they identified a massive circular structure buried beneath the Yucatan Peninsula. The Chicxulub crater, named after a small town near its center, was exactly the right size and age to match the global evidence of the impact. But discovering the crater was just the beginning. Scientists wanted to understand the precise sequence of events that followed the impact. They began drilling deep into the crater structure, extracting cores of rock that told the story of those crucial first hours and days. What they found painted a picture of devastation that exceeded even their most dramatic theories. The drill cores revealed that the impact had created a temporary crater nearly twice the size of the final structure we see today. The initial cavity was so large that it was unstable, causing the crater walls to collapse inward and the center to rebound upward like a droplet of water frozen in time. This process, called complex crater formation, happens only in the most massive impacts. Within the crater, scientists found evidence of the incredible temperatures generated by the impact. Rocks had been melted and then rapidly cooled, creating glass beads called spherules. Some of these glass formations showed clear evidence of having been formed in the vacuum of space before falling back to Earth. The impact had literally blasted material beyond the atmosphere and into orbit. But perhaps the most chilling discovery came from studying the limestone and gypsum rocks that the asteroid had struck. These sedimentary layers contained vast amounts of sulfur compounds that would have been vaporized by the impact, releasing toxic gases into the atmosphere on an unprecedented scale. The sulfur dioxide alone would have been enough to create acid rain 100 times more concentrated than anything produced by modern industrial pollution. Climate models based on this geological evidence revealed the true scope of the catastrophe. The combination of debris blocking sunlight, sulfur compounds creating acid rain, and massive wildfires releasing soot would have created a perfect storm of environmental destruction. Global temperatures would have dropped by as much as 30 degrees Fahrenheit in some regions, while acid rain with a pH similar to battery acid would have poured from the skies for months. The precision of the geological record allowed scientists to reconstruct not just what happened, but when it happened. The impact occurred during late spring or early summer in the Northern Hemisphere, based on the growth patterns of fossilized fish found in North Dakota. These fish had been killed by massive waves triggered by the impact, and their bones preserved the seasonal markers of their final days. Even more remarkably, scientists have been able to determine that the asteroid approached from the northeast at a shallow angle of about 60 degrees. This wasn't a head-on collision, but more like a cosmic drive-by shooting. The shallow angle maximized the amount of debris ejected into the atmosphere, making the impact far more devastating than it would have been if the asteroid had struck straight down. The forensic analysis extends beyond just the physical evidence. Scientists have used computer simulations to model the asteroid's journey through Earth's atmosphere, calculating how much of it would have burned up during its brief but spectacular descent. The models suggest that very little of the original asteroid survived to reach the ground. Most of its mass was vaporized by the incredible friction of atmospheric entry, adding to the global shower of superheated debris. These same models have revealed another disturbing truth. The Chicxulub impactor was actually on the smaller side of asteroids capable of causing mass extinction. Objects half its size could still trigger global catastrophe, while impacts from larger objects would be exponentially more devastating. The dinosaurs were killed by what amounts to a relatively modest cosmic pebble. The story becomes even more precise when we examine the immediate aftermath of the impact. Geological evidence suggests that the first effects were felt within minutes, as seismic waves traveled around the planet. Earthquakes triggered by these waves would have been felt as far away as what is now India, where massive volcanic eruptions were already underway. The timing of these volcanic eruptions, known as the Deccan Traps, has sparked debate among scientists. Some argue that the volcanism was already contributing to environmental stress before the impact, weakening ecosystems and making them more vulnerable to the final blow. Others suggest that the impact may have intensified the volcanic activity, creating a 1-2 punch of catastrophes. What's clear from the rock record is that the recovery from the impact was anything but uniform. In some locations, evidence suggests that plant life began returning within decades of the impact. In others, particularly areas that had been heavily affected by acid rain, the landscape remained barren for thousands of years. The fossil record of the recovery period reveals fascinating insights into how evolution responds to sudden opportunity. Small mammals that had been restricted to nocturnal lifestyles suddenly diversified into day-active forms. Within just a few million years of the impact, mammals had evolved into forms as large as modern bears, filling ecological niches that had been occupied by dinosaurs for over 100 million years. But the most remarkable aspect of the post-impact world was the explosion of flowering plants. During the Cretaceous, flowering plants had been present but not dominant. Ferns, conifers, and other more primitive plants had covered most of the landscape. The impact winter and acid rain had been particularly devastating to these established plant communities, creating opportunities for the more adaptable flowering plants to take over. This botanical revolution had cascading effects throughout the ecosystem. Flowering plants created new opportunities for pollinating insects, which in turn supported new types of insectivorous mammals and birds. The co-evolution of flowering plants and their pollinators became one of the driving forces behind the diversification of life in the post-impact world. Scientists have also discovered that the impact may have had unexpected long-term benefits for life on Earth. The massive crater created a unique environment that became a hotspot for the evolution of new species. The central peak of the crater, formed during the rebound process, brought deep crustal rocks to the surface, creating new mineral environments that some organisms learned to exploit. Even today, the Chicxulub crater continues to influence the geology of the Yucatan Peninsula. The circular pattern of underground rivers and sinkholes, called cenotes, follows the outline of the ancient crater rim. These water-filled caverns have become windows into the past, preserving fossils and geological evidence from the impact and its aftermath. Modern drilling projects continue to extract new information from the crater. In recent years, scientists have drilled into the peak ring of the crater, retrieving rock samples that were formed in the minutes and hours immediately following the impact. These cores contain a minute-by-minute record of the most catastrophic day in Earth's history, preserved in stone like a geological time capsule. The research has revealed that life returned to the crater surprisingly quickly. Within just a few 100,000 years of the impact, the crater had become a thriving marine ecosystem. Tiny marine organisms began building new reefs on top of the impact debris, literally constructing new life on the foundation of mass extinction. This rapid recovery challenges our understanding of how quickly ecosystems can bounce back from catastrophic events. While it took millions of years for global biodiversity to fully recover from the impact, local ecosystems could apparently re-establish themselves much more quickly than previously thought. The Chicxulub research has also provided crucial insights into the mechanics of mass extinction itself. Scientists now understand that the key to survival wasn't necessarily being the strongest or the smartest, but being the most adaptable to rapidly changing conditions. Small body size, generalized diets, and the ability to hibernate or go dormant were far more valuable than specializations that had worked for millions of years. This understanding has profound implications for modern conservation efforts. As human activities create environmental pressures that some scientists compare to a sixth mass extinction, the lessons from Chicxulub suggest that the species most likely to survive are those that can adapt quickly to changing conditions, rather than those that are highly specialized for current environments. The asteroid that killed the dinosaurs also fundamentally changed the chemistry of Earth's oceans and atmosphere. The impact added significant amounts of carbon to the atmosphere, not just from the vaporized asteroid itself, but from the massive wildfires that followed. This carbon pulse can still be detected in rock layers around the world, providing a global marker of the impact event. The ocean chemistry changes were equally dramatic. The massive die-off of marine plankton disrupted the biological carbon pump that moves carbon from the surface waters to the deep ocean. This disruption lasted for hundreds of thousands of years, fundamentally altering global carbon cycles in ways that affected climate long after the immediate effects of the impact had faded. Scientists have also discovered that the impact may have triggered changes in Earth's magnetic field. The tremendous energies involved in the impact were sufficient to affect the flow of molten iron in Earth's outer core, potentially influencing the magnetic field that protects our planet from harmful cosmic radiation. These magnetic field changes, if they occurred, would have had subtle but important effects on the evolution of life in the post-impact world. Increased cosmic radiation could have accelerated mutation rates, potentially speeding up the evolutionary changes that led to the rapid diversification of mammals and flowering plants. The precision with which scientists can now reconstruct the Chicxulub impact represents one of the greatest achievements in Earth science. From a thin layer of clay discovered in Italian rocks, researchers have built a detailed picture of the most important single event in the history of complex life on Earth. But the story of Chicxulub is far from over. Each new drilling project, each new computer simulation, each new fossil discovery adds another piece to the puzzle. Scientists are still working to understand exactly why some groups of organisms survived while others perished, and how the specific environmental changes triggered by the impact led to the evolutionary explosion that followed. The implications of this research extend far beyond academic curiosity. Understanding how life responds to sudden catastrophic environmental change provides crucial insights into how modern ecosystems might respond to rapid climate change, habitat destruction, and other human-induced environmental pressures. The Chicxulub impact also serves as a stark reminder of Earth's place in a dynamic and sometimes violent universe. While the dinosaurs had no way to predict or prepare for their cosmic executioner, we have developed the technology to track potentially dangerous asteroids and, at least in theory, to deflect them before they reach Earth. This capability represents an unprecedented moment in the history of life on our planet. For the first time, a species has evolved the intelligence and technology to potentially prevent its own extinction from cosmic impacts. Whether we choose to use this capability wisely remains to be seen. The story of the day the dinosaurs died is ultimately a story about the power of scientific investigation to reveal truths about our planet's past that no human witnessed firsthand. Through careful analysis of rocks, fossils, and chemistry, scientists have reconstructed one of the most dramatic events in Earth's history with remarkable precision and detail. But perhaps most importantly, the Chicxulub impact reminds us that we are all products of catastrophe. Every mammal alive today, including humans, owes its existence to the cosmic accident that ended the age of dinosaurs and opened evolutionary pathways that had been closed for over 100 million years. We are the children of the asteroid impact, the inheritors of a world remade by cosmic violence, the beneficiaries of the most terrible day in our planet's history. And in that terrible irony lies both the fragility and the resilience that define life itself. The story of how we came to understand the Chicxulub impact reveals something profound about the nature of scientific discovery. It shows us that the most important truths about our world are often hidden in the most mundane places, waiting for the right eyes to see them and the right minds to piece together their meaning. But there's another layer to this story that's equally fascinating. The impact that killed the dinosaurs didn't just reshape life on Earth, it fundamentally altered the planet's evolutionary trajectory in ways that are still playing out today. To understand how profound this change was, we need to imagine what Earth might have looked like if that asteroid had missed our planet by just a few thousand miles. Picture a world where the great tyrannosaurs continued their reign for another 60 million years, where massive sauropods still thundered across ancient landscapes, their calls echoing through valleys that would never know the sound of human voices, where the skies remained the domain of pterosaurs, and mammals stayed small, nocturnal creatures hiding in the shadows of giants. This alternate Earth would be unrecognizable to us. There would be no grasslands stretching to the horizon because grasses were rare during the age of dinosaurs. No deciduous forests painting autumn landscapes in brilliant colours because flowering trees were still evolutionary newcomers. No herds of large mammals migrating across continents because those ecological niches belonged to dinosaurs. Most importantly for our story, there would be no primates. No curious apes learning to use tools. No species capable of looking up at the night sky and wondering about its place in the cosmos. The cognitive revolution that gave birth to human consciousness might never have occurred in a world still dominated by reptilian intelligence. But the asteroid didn't miss. It struck with perfect, terrible precision. And in doing so, it didn't just end one chapter of Earth's story, it began writing an entirely new book. The world that emerged from the ashes of the Cretaceous was more than just different from what came before. It was revolutionary. Consider the explosion of mammalian diversity that followed the extinction. During the Cretaceous, most mammals were no larger than rats. They lived in the ecological margins, active only at night when the great dinosaurs slept. But within just 10 million years of the impact, mammals had diversified into forms that would have seemed impossible in the dinosaur-dominated world. Some grew to enormous sizes, filling the ecological roles once occupied by large dinosaurs. Others took to the water, beginning the evolutionary journey that would eventually produce whales and dolphins. Still others developed specialized diets and behaviors that had never existed before. The mammalian explosion wasn't just about filling empty niches, it was about creating entirely new ways of being alive. This diversification wasn't random. It followed patterns that revealed deep truths about how evolution responds to opportunity. When ecological space opens up suddenly, life doesn't just expand, it experiments. It tries new combinations, new strategies, new solutions to the ancient problems of survival and reproduction. The early mammals that inherited the post-impact world were evolutionary pioneers in the truest sense. They were exploring territories of biological possibility that had been closed off for over 100 million years. Some of these experiments failed, leading to evolutionary dead ends that we know only from fossils. But others succeeded spectacularly, giving rise to lineages that would eventually produce everything from tiny shrews to massive elephants, from soaring bats to diving seals. But perhaps the most significant change wasn't in the animals themselves, but in the plants that form the foundation of terrestrial ecosystems. The impact winter and acid rain had been particularly devastating to the established plant communities of the Cretaceous. Ferns, conifers, and other groups that had dominated landscapes for hundreds of millions of years suddenly found themselves at a severe disadvantage. Into this botanical void stepped the flowering plants. These relatively new arrivals had been present during the Cretaceous, but had never achieved true dominance. The post-impact world gave them their chance, and they seized it with remarkable success. Within a few million years, flowering plants had transformed from minor players to the dominant force in terrestrial ecosystems. This botanical revolution had cascading effects that are still shaping our world today. Flowering plants created new opportunities for pollinating insects, leading to the co-evolutionary partnerships between plants and pollinators that give us everything from colourful wildflower meadows to fruit-bearing trees. They developed new strategies for seed dispersal, creating the complex relationships with animals that characterize modern ecosystems. Most importantly for our own species, the rise of flowering plants set the stage for the evolution of grasslands. During the dinosaur age, open plains were relatively rare. Most terrestrial landscapes were covered by forests of ferns and conifers. But in the post-impact world, grasses began to spread across vast areas, creating entirely new types of ecosystems. These grasslands became the foundation for some of the most spectacular examples of mammalian evolution. The great herds of grazing animals that once migrated across continents, the predators that followed them, the complex ecological relationships that developed in these open landscapes. All of this was made possible by the botanical changes that followed the Chicxulub impact. But the changes went even deeper than individual species or even entire ecosystems. The impact fundamentally altered the way evolution itself operates on our planet. In the dinosaur-dominated world, evolutionary change was often slow and incremental. Established groups maintained their dominance for millions of years, with relatively little opportunity for dramatic innovation. The mass extinction changed that. It created what evolutionary biologists call an adaptive radiation, a period of rapid diversification when many new ecological niches become available simultaneously. These periods are like evolutionary explosions, times when life experiments with new forms and functions at an accelerated pace. The mammalian radiation that followed the Chicxulub impact was one of the most dramatic adaptive radiations in Earth's history. But it wasn't just mammals that benefited from the evolutionary opportunities created by the extinction. Birds already reified into forms that had never existed before the survivors among dinosaur groups, divers. Some grew to enormous sizes, becoming the apex predators of the early post-impact world. Others developed specialized feeding strategies or flight capabilities that opened up new ecological possibilities. Even plants participated in this evolutionary explosion. The flowering plants that came to dominate post-extinction landscapes weren't just more successful versions of their Cretaceous predecessors. They were fundamentally new types of organisms with novel strategies for survival and reproduction. This pattern of post-extinction innovation reveals something profound about the relationship between destruction and creation in the natural world. Mass extinctions aren't just endings, they're also beginnings. They clear away the established order and create space for evolutionary experimentation on a scale that's impossible during periods of ecological stability. The Chicxulub impact was the ultimate example of this process. It didn't just kill the dinosaurs, it reset the evolutionary game entirely. The rules that had governed life on Earth for over 100 million years were suddenly obsolete, replaced by new challenges and new opportunities that favored very different survival strategies. This reset had implications that extended far beyond the immediate post-impact period. The evolutionary innovations that emerged in the aftermath of the extinction continued to shape life on Earth for millions of years. The mammalian body plans that evolved in the early Paleocene provided the foundation for all subsequent mammalian evolution. The plant-animal relationships that developed in post-extinction ecosystems created the template for modern terrestrial food webs. But perhaps most remarkably, the impact created the conditions that would eventually allow for the evolution of intelligence itself. The mammalian radiation that followed the extinction included the early primates, small arboreal creatures that developed enhanced visual systems and manipulative abilities as adaptations to life in the trees. These early primates weren't particularly impressive by the standards of their time. They were small, relatively simple creatures that would have seemed insignificant compared to the large mammals that dominated post-extinction landscapes. But they carried within their genes the potential for something unprecedented in Earth's history, the evolution of consciousness. The pathway from these early primates to modern humans was neither direct nor inevitable. It involved millions of years of evolutionary experimentation, countless dead ends, and at least a few more near extinctions. But the crucial point is that this pathway was opened by the Chicxulub impact. Without the extinction of the dinosaurs, the ecological opportunities that led to primate evolution might never have existed. This brings us to one of the most profound ironies in the history of life on Earth. The event that seemed like the ultimate catastrophe was actually the ultimate creative force in our planet's biological history. The asteroid that brought darkness and death to the Cretaceous world also brought the possibility of consciousness, of art, of science, of all the things that make human existence meaningful. We are, in a very real sense, the children of catastrophe. Our existence is a direct consequence of cosmic violence, of the most terrible day in our planet's history. Every human achievement, every work of art, every scientific discovery, every moment of love and joy and wonder, all of it traces back to that moment 66 million years ago, when a mountain of rock and metal fell from the sky and changed everything. But the story doesn't end there. The impact that created the conditions for our evolution also serves as a reminder of our place in a universe that is both creative and destructive, nurturing and hostile. The same cosmic processes that made our existence possible could also end it. The universe that gave birth to consciousness through catastrophe remains capable of destroying it through catastrophe. This understanding has profound implications for how we think about our species and our future. We are not the inevitable product of evolutionary progress, destined to inherit the Earth through some cosmic plan. We are the unlikely survivors of cosmic accident, the beneficiaries of destruction, the inheritors of a world remade by forces beyond our control. Yet this knowledge also gives us power. Unlike the dinosaurs, we can see our cosmic threats coming. We have developed the technology to track potentially dangerous asteroids and, at least in theory, to deflect them before they reach Earth. We have the capability to become the first species in Earth's history to prevent its own extinction from cosmic impacts. This capability represents a turning point in the relationship between life and the cosmos. For over 4 billion years, life on Earth has been subject to the whims of celestial mechanics, vulnerable to destruction from space without warning or defense. The evolution of human intelligence and technology has, for the first time, given life the power to defend itself against cosmic threats. But with this power comes responsibility. The same intelligence that allows us to track asteroids and plan planetary defense also gives us the ability to understand our place in the larger story of life on Earth. We know that we are the products of mass extinction, that our existence depends on the continued stability of the biosphere that the Chicxulub impact helped create. This knowledge should humble us. We are not separate from nature, not above the evolutionary processes that shaped us. We are part of the ongoing story of life on Earth, temporary custodians of the consciousness that emerged from the ashes of the Cretaceous extinction. How we use this consciousness, what we do with the remarkable capabilities it has given us, will determine not just our own fate, but the fate of countless other species that share our planet. The asteroid that killed the dinosaurs teaches us that life is both incredibly fragile and astonishingly resilient. It shows us that even the most successful organisms, even the most stable ecosystems, can disappear in an instant when faced with forces beyond their control. But it also shows us that life itself is persistent, creative, and capable of recovering from even the most devastating catastrophes. We stand at a unique moment in this ongoing story. We are perhaps the first species in Earth's history to fully understand the cosmic forces that have shaped life on our planet. We know about mass extinctions, about asteroid impacts, about the deep time processes that have governed the evolution of life for billions of years. This knowledge gives us both privilege and burden. We have the privilege of consciousness, of being able to contemplate our own existence and our place in the cosmos. But we also have the burden of responsibility, of being the first species capable of consciously directing the future course of evolution on our planet. The choices we make in the coming decades and centuries will echo through deep time, just as the Chicxulub impact continues to echo through the 66 million years since it occurred. We have the power to be either the asteroid or the survivors, the force of destruction or the agents of renewal. The dinosaurs had no choice in their fate. The cosmic bullet that ended their reign was beyond their ability to predict or prevent. But we do have choices. We can choose to use our intelligence to protect our planet from cosmic threats. We can choose to preserve the biodiversity that evolution has created. We can choose to be good ancestors to the species that will inherit the Earth after we are gone. The story of the Chicxulub impact is ultimately our story. It explains how we came to exist, why our world looks the way it does, and what forces continue to shape the evolution of life on our planet. But more than that, it provides a framework for understanding our responsibilities as the inheritors of a world remade by catastrophe. We are living in the aftermath of the most important event in the history of complex life on Earth. Every breath we take, every step we make, every thought we think is possible because of what happened on that terrible day 66 million years ago. The question now is what we will do with this knowledge, and what kind of world we will leave for the species that come after us. The asteroid may have ended the age of dinosaurs, but it also began the age of possibility. What we make of that possibility is up to us. The immediate aftermath of the impact was a sequence of horrors that unfolded with mechanical precision. Within the first few seconds, as the asteroid vaporized into superheated plasma, it created what scientists call a transient cavity. This wasn't just a hole in the ground. It was a temporary wound in the Earth's crust, so massive that the planet's own gravity couldn't hold it open. The rocks at the impact site didn't just melt. They were shocked into entirely new mineral forms that exist nowhere else on Earth, except at nuclear test sites and other impact craters. Quartz crystals were compressed so violently that their atomic structure was permanently deformed, creating microscopic evidence of pressures exceeding anything found in normal geological processes. But the true scale of devastation becomes clear when we follow the seismic waves that radiated outward from ground zero. These weren't ordinary earthquakes. The impact generated seismic energy equivalent to a magnitude 10 or 11 earthquake, far beyond anything recorded in human history. To put this in perspective, the most powerful earthquake ever measured was magnitude 9.5. The Chicxulub impact was at least 10 times more powerful. These seismic waves travelled through the Earth's crust at speeds approaching 4 miles per second. As they spread outward, they triggered landslides, collapsed cave systems, and may have destabilized fault lines thousands of miles away. In some regions, the ground literally liquefied as soil and rock lost their structural integrity under the oscillating pressure waves. The seismic effects were particularly devastating along coastlines. As the shock waves reached the ocean floor, they triggered underwater landslides that generated tsunamis of unprecedented scale. These weren't the relatively modest waves we associate with even the most destructive modern tsunamis. Computer models suggest that some of these impact-generated waves may have reached heights of over 300 feet, carrying marine sediments hundreds of miles inland. Evidence of these massive waves can still be found in rock formations across North America. In places like North Dakota and Colorado, geologists have discovered layers of marine fossils mixed with terrestrial debris, deposited far from any ancient coastline. These jumbled fossil beds tell the story of waves so powerful they could transport ocean life deep into continental interiors. The atmospheric effects began almost immediately after impact. As trillions of tons of rock were blasted into the sky, much of this material followed ballistic trajectories that carried it far beyond the atmosphere before it fell back to Earth. This created a global phenomenon unlike anything in recorded history, a planet-wide meteor shower of impact debris. As this material re-entered the atmosphere, friction heated it to temperatures exceeding 1,500 degrees Celsius. The sky didn't just glow, it became a radiant heat source that could ignite organic material simply through thermal radiation. Any animal caught in the open during this global firestorm would have experienced conditions similar to being inside a giant oven. The thermal pulse lasted for hours, possibly days in some regions. During this time, forests that had stood for millions of years burst into flames simultaneously across multiple continents. The Amazon basin of the Cretaceous, the great coniferous forests of what would become North America, the fern prairies of ancient Asia, all of them ignited in a synchronized conflagration that turned the entire planet into a furnace. But fire was only the beginning. As the debris continued to rain from the sky, it began to accumulate in the upper atmosphere, forming a global shroud that blocked increasing amounts of sunlight. This wasn't a gradual process. Computer simulations suggest that light levels may have dropped by 90% or more within the first few days after impact. The psychological impact on surviving animals would have been profound. Creatures that had never experienced prolonged darkness suddenly found themselves in a world where day and night became meaningless concepts. Diurnal animals, including many dinosaurs, would have been particularly vulnerable to this disruption of circadian rhythms. The temperature effects followed quickly. Without sunlight to warm the surface, global temperatures began to plummet. The impact winter wasn't a slow seasonal change. It was a rapid descent into conditions more severe than any ice age in Earth's history. In some regions, temperatures may have dropped 30 degrees Celsius within weeks of the impact. This sudden freeze had cascading effects throughout terrestrial ecosystems. Plants that had evolved in warm, stable climates found themselves facing conditions they had no evolutionary preparation for. Even cold-adapted species struggled because the change was too rapid for normal acclimatization processes. The marine environment faced its own unique catastrophe. As sulfur-rich rocks vaporized at the impact site, they released massive quantities of sulfur dioxide into the atmosphere. When this gas mixed with atmospheric water vapor, it formed sulfuric acid droplets that eventually fell as acid rain with a pH approaching that of battery acid. Ocean chemistry, which had remained relatively stable for millions of years, shifted dramatically within months of the impact. The acid rain didn't just affect surface waters, it penetrated deep into marine ecosystems, dissolving the calcium carbonate shells of countless organisms and disrupting food chains from the bottom up. Microscopic marine plankton, the foundation of ocean food webs, began dying en masse. These tiny organisms had been removing carbon dioxide from the atmosphere and producing oxygen for hundreds of millions of years. Their sudden collapse not only disrupted marine ecosystems, but also began altering the planet's atmospheric chemistry in ways that would persist for millennia. The collapse of marine food webs had immediate effects on larger organisms. Fish populations crashed as their food sources disappeared. Marine reptiles, many of which had been apex predators in Cretaceous seas, found themselves in oceans that could no longer support them. The great mosasaurs and plesiosaurs that had ruled the waves for millions of years faced starvation in waters turned toxic and barren. On land, the situation was equally dire. As plants died from the combination of darkness, cold, and acid rain, herbivorous dinosaurs faced mass starvation. These weren't creatures adapted for lean times. Many Cretaceous herbivores were enormous animals that required vast quantities of plant matter to survive. When their food sources disappeared, they had no evolutionary backup plan. The great sauropods, some weighing over 70 tons, needed to consume hundreds of pounds of vegetation daily just to maintain their basic metabolic functions. In the post-impact world, such quantities of food simply didn't exist. These gentle giants, which had successfully adapted to changing climates for over 150 million years, found themselves facing a challenge that their enormous size had made insurmountable. Carnivorous dinosaurs faced their own crisis as herbivore populations collapsed. The great tyrannosaurs, perfectly adapted for hunting large prey, suddenly found themselves in a world with little large prey to hunt. Their massive size, which had been an advantage in the arms race between predator and prey, became a liability when food became scarce. Smaller predators had some advantages in the New World. They required less food and could potentially survive on carrion from the mass die-offs. But even these more adaptable carnivores faced challenges that tested the limits of their survival abilities. The combination of cold temperatures, toxic air, and scarce prey created a perfect storm of selection pressure. Yet even in this global catastrophe, life found ways to persist. The survivors weren't necessarily the strongest or most sophisticated organisms. They were often the most humble, the most adaptable, the ones that had always lived on the margins of Cretaceous ecosystems. Small mammals, which had spent over 100 million years in the shadows of dinosaur-dominated ecosystems, suddenly found their modest requirements and flexible behaviors to be tremendous advantages. Their ability to burrow provided protection from temperature extremes and toxic conditions. Their omnivorous diets allowed them to survive on whatever organic matter remained available. Many of these mammalian survivors were no larger than modern rats or shrews. They had fast reproductive cycles, which meant that populations could recover quickly from losses. They were often nocturnal, which gave them experience navigating in low-light conditions. Most importantly, they were generalists rather than specialists, able to adapt their behavior and diet to changing circumstances. The birds that survived the extinction shared many of these characteristics. The avian survivors were generally small-bodied species with flexible diets and the ability to fly to new areas when local conditions became untenable. Their feathers provided insulation against the cold, and their relatively low food requirements helped them survive when resources were scarce. But survival, in the immediate aftermath of the impact, was only the first challenge. The real test came in the months and years that followed, as the planet began its slow recovery from the most catastrophic event in the history of complex life. The world that emerged from this crucible would be fundamentally different from anything that had existed before, setting the stage for evolutionary experiments on a scale never before seen in Earth's history. The recovery process began in the most unlikely places. In deep ocean sediments bacterial communities that had been dormant for millennia began to stir. These microorganisms, adapted to extreme conditions, found themselves in a world suddenly suited to their particular survival strategies. As they multiplied, they began the slow process of restoring basic ecosystem functions. On land, the first signs of recovery appeared in areas with abundant freshwater sources. Small pools and streams that had somehow avoided the worst of the acid rain became refugia where simple organisms could begin rebuilding biological communities. Algae and bacteria formed the foundation of these recovery ecosystems, creating the conditions necessary for more complex organisms to eventually return. The fungal networks that had quietly operated in forest soils for millions of years suddenly found themselves in an unprecedented opportunity. The global wildfires had created the largest deposit of dead organic matter in Earth's history. As fungi spread through this material, they began breaking it down and recycling nutrients back into the soil, preparing the ground for the eventual return of plant life. This process of biological recycling was crucial to the planet's recovery. Without decomposer organisms to break down the massive amounts of dead plant and animal material, the post-impact world might have remained sterile for much longer. The humble fungi and bacteria that accomplished this task were perhaps the unsung heroes of Earth's recovery story. As conditions slowly stabilized, the first pioneer plant species began to appear. These weren't the towering trees or lush ferns of the Cretaceous. They were small, hardy species adapted to poor soil conditions and variable climate. Many were what botanists call weedy species, plants that specialize in colonizing disturbed habitats. These pioneer plants played a crucial role in ecosystem restoration. Their roots helped stabilize soil that had been loosened by the impact effects. Their photosynthesis began the slow process of removing excess carbon dioxide from the atmosphere. Most importantly, they created the foundation upon which more complex plant communities could eventually develop. The animal recovery followed the plant recovery, but it didn't simply restore what had existed before. Instead, it created entirely new types of ecological relationships. Small mammals that had once been restricted to nocturnal lifestyles began exploring diurnal niches that had been vacated by dinosaurs. Some developed new feeding strategies, becoming specialized seed eaters as grasses and flowering plants began to spread. The evolutionary innovations that emerged during the recovery period were remarkable in their creativity. Some early mammals developed enhanced digging abilities, allowing them to exploit underground resources that had been inaccessible to surface-dwelling dinosaurs. Others evolved improved climbing skills, taking advantage of the three-dimensional habitat provided by recovering forests. But perhaps the most significant changes occurred in the plant communities themselves. The flowering plants that had been relatively minor players during the Cretaceous found themselves with unprecedented opportunities in the post-impact world. They diversified rapidly, developing new strategies for survival and reproduction that would eventually make them the dominant force in terrestrial ecosystems. This botanical revolution created cascading effects throughout the recovery ecosystems. New types of plant-animal relationships evolved as mammals and insects learned to exploit the resources provided by flowering plants. The co-evolutionary partnerships between plants and their pollinators, which are so characteristic of modern ecosystems, had their origins in this post-extinction period. The recovery wasn't uniform across the planet. Some regions, particularly those that had been hit hardest by the immediate impact effects, remained barren for hundreds of thousands of years. But in other areas, life rebounded with surprising speed. Within just a few 100,000 years, some ecosystems had achieved levels of complexity that rivaled those of the pre-impact world. This variability in recovery patterns created a patchwork of different evolutionary experiments across the planet. In regions where recovery was rapid, intense competition drove rapid evolutionary change. In areas where recovery was slow, The few surviving species had opportunities to diversify into multiple ecological roles without competition. The stage was now set for one of the most remarkable periods in the history of life on Earth. The extinction had cleared the evolutionary slate, removing the dominant groups that had controlled terrestrial ecosystems for over 160 million years. In their place, a new cast of characters was preparing to take the stage, ready to write the next chapter in the story of life on our planet. The transformation that followed wasn't just biological, it was fundamentally architectural. If you could have stood on Earth 10 million years after the impact and looked around, you would have been witnessing the construction of an entirely new type of planet. The rules of engagement between predator and prey, between plant and pollinator, between organism and environment, were being rewritten in real time. Consider what had happened to the very concept of size in terrestrial ecosystems. For over 160 million years, bigger had generally meant better. The largest herbivores could reach the tallest vegetation. The largest carnivores could take down the largest prey. Size was power, and power meant evolutionary success. The Chicxulub impact shattered this fundamental rule. In the post-impact world, being large became a liability almost overnight. Large animals needed more food, more space, more stable conditions. They reproduced slowly and couldn't adapt quickly to changing circumstances. The new world belonged to the small, the fast, the flexible. This wasn't just a temporary adjustment. It was a permanent rewiring of how evolution would operate on our planet. The mammals that began to diversify in this new world were evolutionary opportunists in the purest sense. They didn't just fill the empty ecological niches left by dinosaurs. They invented entirely new ways of making a living. Some became specialized diggers, creating underground networks that had never existed before. Others developed the ability to glide between trees, exploiting three-dimensional space in ways that ground-dwelling dinosaurs never could. But perhaps most remarkably, some early mammals began experimenting with something that had been virtually unknown in the dinosaur world: sophisticated social behavior. While some dinosaurs may have lived in groups, the complex social structures that would eventually characterize mammalian societies were largely a post-impact innovation. The harsh conditions of the recovery period favored animals that could cooperate, share information, and coordinate their survival strategies. This social revolution had profound implications for the development of intelligence. Animals that lived in complex social groups needed to be able to remember relationships, predict the behavior of others, and navigate intricate hierarchies. These cognitive demands drove the evolution of larger, more sophisticated brains. The pathway to human intelligence, while still millions of years in the future, was being paved in the earliest post-impact mammalian communities. The plant world was undergoing its own revolution. The flowering plants that inherited the post-extinction landscape weren't content to simply replace the ferns and conifers that had dominated before. They began experimenting with entirely new strategies for capturing sunlight, conserving water, and reproducing. Some developed the ability to change their leaf structure seasonally, creating the deciduous forests that would become one of the most characteristic features of the post-impact world. Others began forming partnerships with animals in ways that had been rare during the dinosaur age. The evolution of fruits, for example, represented a revolutionary bargain between plants and animals. Plants would provide nutritious, attractive packages of food in exchange for animals dispersing their seeds to new locations. This partnership would eventually reshape both plant and animal evolution in ways that are still unfolding today. The insect world exploded with new forms and functions. With flowering plants providing new sources of nectar and pollen, insects diversified into an astonishing array of specialized pollinators. Bees, butterflies, and countless other pollinating insects evolved complex relationships with specific plant species. These partnerships created feedback loops that drove both plant and insect evolution toward ever greater complexity and specialization. But the most profound change may have been one that was invisible to any observer at the time. The rewiring of Earth's chemical cycles. The massive forests of the Cretaceous had stored enormous amounts of carbon in their wood and leaves. When these forests burned in the impact fires, much of this carbon was released back into the atmosphere. The new plant communities that emerged had very different carbon storage strategies. Grasses, which became increasingly important in post-impact ecosystems, stored much of their carbon underground in extensive root systems. This created a more stable, long-term carbon sink than the above-ground storage systems of Cretaceous forests. The shift toward grass-dominated landscapes fundamentally altered Earth's carbon cycle in ways that would influence global climate for millions of years. The ocean recovery was equally dramatic, but followed very different patterns. Marine ecosystems had been devastated not just by the acid rain and temperature changes, but by the collapse of the microscopic organisms that formed the base of oceanic food webs. The recovery began with these tiny creatures, but it didn't simply restore what had existed before. New types of plankton evolved with different feeding strategies and chemical tolerances. Some developed the ability to form protective cysts that could survive harsh conditions, while others evolved more efficient ways of extracting nutrients from seawater. These changes at the microscopic level rippled upward through marine food webs, creating entirely new types of oceanic ecosystems. The few marine reptiles that survived the extinction found themselves in seas that operated by different rules. The massive mosasaurs and long-necked plesiosaurs were gone forever, but smaller marine reptiles began diversifying into new ecological roles. Some became specialized fish eaters. Others evolved to hunt in the deep ocean, and a few began the evolutionary journey that would eventually lead back to land. But perhaps the most significant marine recovery story belongs to a group that barely existed during the dinosaur age: whales. The earliest whale ancestors were small, four-legged mammals living along coastlines in the early post-impact world. Over the course of millions of years, some of these mammals began spending more time in the water, eventually evolving into fully aquatic creatures that would come to dominate oceanic ecosystems in ways that marine reptiles never had. This transition from land to sea represents one of the most remarkable evolutionary transformations in Earth's history. It shows how the opportunities created by mass extinction can lead to entirely new evolutionary experiments. The whales that eventually evolved weren't just marine versions of terrestrial mammals. They developed unique adaptations like echolocation and complex social behaviors that had no precedent in the dinosaur-dominated seas of the Cretaceous. The recovery process also reveals something crucial about the nature of evolutionary innovation. The most successful post-extinction organisms weren't necessarily the ones that most closely resembled their extinct predecessors. Instead, they were often the ones that developed entirely new solutions to the challenges of survival. This pattern of innovation through catastrophe would become a recurring theme in Earth's evolutionary history. The speed of this transformation is perhaps its most remarkable aspect. While geological processes typically unfold over millions or tens of millions of years, the post-Chicxulub recovery happened in evolutionary fast-forward. Within just 5 to 10 million years, Earth's ecosystems had not only recovered their pre-impact levels of diversity, but had developed entirely new forms of complexity. This rapid pace of change was driven partly by the empty ecological space left by the extinction, but also by the new types of environmental challenges that survivors faced. The post-impact world was more variable, more unpredictable than the stable greenhouse conditions that had characterized much of the Cretaceous. This variability favored organisms that could adapt quickly to changing conditions. The climate itself became a driver of evolutionary innovation. Instead of the relatively stable, warm conditions that had persisted for millions of years, the post-impact world experienced more dramatic swings between warm and cool periods. These climate oscillations created selective pressures that favored behavioral flexibility and physiological adaptability over narrow specialization. Some of the most significant evolutionary innovations of this period were responses to these new climate challenges. The evolution of hibernation, for example, allowed small mammals to survive seasonal food shortages that would have been fatal to their Cretaceous ancestors. The development of migration behaviors enabled animals to track resources across landscapes that were no longer uniformly habitable. But perhaps the most important innovation was the evolution of what scientists call phenotypic plasticity, the ability of individual organisms to change their characteristics in response to environmental conditions. This wasn't genetic evolution happening between generations. This was individuals changing their behavior, physiology, or even anatomy during their own lifetimes in response to environmental cues. This type of flexibility was virtually unknown in the dinosaur world, where most species were highly specialized for specific environmental conditions. The post-impact world favored generalists, organisms that could adjust their strategies as conditions changed. This flexibility would become one of the defining characteristics of mammalian evolution and would eventually contribute to the evolution of intelligence itself. The psychological implications of living in this rapidly changing world were profound. Animals that had once been able to rely on instinctual behaviors, passed down through millions of years of evolution, now had to learn, adapt, and innovate within their own lifetimes. This created selective pressure for larger brains, better memory, and more sophisticated learning abilities. The early primates that emerged during this period were products of this new evolutionary environment. Their enhanced visual systems, manipulative abilities, and social behaviors were all adaptations to a world that demanded flexibility and intelligence. While they were still millions of years away from developing human-level consciousness, they carried within their neural architecture the seeds of the cognitive revolution that would eventually lead to language, art, and science. The transformation of Earth's ecosystems in the aftermath of the Chicxulub impact represents more than just biological recovery. It represents the birth of the modern world. The grasslands that support global agriculture, the forests that regulate climate, the marine ecosystems that feed billions of people. All of these trace their origins back to the evolutionary innovations that emerged from the ashes of the Cretaceous extinction. But this transformation also reveals something profound about the relationship between destruction and creation in the natural world. The impact that seemed like the ultimate catastrophe was actually the ultimate creative force in our planet's history. It didn't just clear away the old world. It created the conditions necessary for entirely new forms of life to emerge. This pattern of creative destruction operates at multiple scales in the natural world. Forest fires clear away old growth and create opportunities for new plant communities. Volcanic eruptions destroy existing landscapes but create new soil that supports novel ecosystems. Even individual deaths contribute to the creative process by returning nutrients to the soil that support new life. The Chicxulub impact was simply the largest example of this fundamental principle. It shows us that catastrophe and creation are not opposites, but partners in the ongoing dance of evolution. The most terrible events in Earth's history have also been the most creative, opening pathways to forms of life that would never have existed otherwise. This understanding has profound implications for how we think about our own species and our place in the ongoing story of life on Earth. We are not the culmination of evolutionary progress, destined to inherit the planet through some cosmic plan. We are the products of catastrophe, the unlikely survivors of destruction, the beneficiaries of the most terrible day in our planet's history. Yet this knowledge also reveals our unique responsibility. We are the first species in Earth's history to understand the forces that shaped us. We know about mass extinctions, about the role of catastrophe in driving evolutionary innovation, about the deep time processes that continue to shape life on our planet. This knowledge gives us both privilege and burden. We have the privilege of consciousness, of being able to contemplate our own existence and our place in the cosmos. But we also have the burden of choice. Unlike the dinosaurs, we can see potential catastrophes coming. We have the technology to track asteroids, to monitor climate change, to understand the environmental pressures that are reshaping ecosystems around the world. The question is what we will do with this knowledge. Will we use our understanding of Earth's history to become better stewards of the planet that catastrophe created for us? Will we learn from the innovations that emerged from past extinctions to help life navigate the challenges of the present? Or will we become the catastrophe ourselves, the force of destruction that clears the way for whatever comes next? The story of the Chicxulub impact and its aftermath suggests that life will continue regardless of what we choose. Evolution is patient, creative, and persistent. It has survived impacts, volcanic eruptions, ice ages, and countless other challenges over billions of years. It will likely survive us as well, whether we choose to be partners in the creative process or simply another chapter in the long history of extinction and renewal. But for the first time in Earth's history, one species has the power to consciously influence the direction of that creative process. We can choose to preserve the biodiversity that evolution has created. We can choose to protect the ecosystems that emerged from past catastrophes. We can choose to use our intelligence and technology to help a life flourish, rather than simply to serve our own immediate needs. The mammals that inherited the post-Chicxulub world were evolutionary pioneers, exploring new territories of biological possibility that had been closed for over 100 million years. Today, we are the inheritors of their legacy, the products of their innovations, the beneficiaries of their survival. The question is, what kind of pioneers we will choose to be. Human beings stand at a unique moment in the history of life on Earth. We are perhaps the first species to fully understand the cosmic and geological forces that have shaped our planet. We know about the asteroid impact that ended the age of dinosaurs. We understand the evolutionary processes that led to our own existence. We can see the environmental changes that are currently reshaping ecosystems around the world. This knowledge gives us unprecedented power to influence the future course of evolution on our planet. We can choose to be agents of conservation, preserving the biological heritage that billions of years of evolution have created. We can choose to be agents of restoration, helping damaged ecosystems recover from human impacts. We can even choose to be agents of innovation, using our technology to create new possibilities for life to flourish. But we can also choose to ignore this knowledge, to continue living as if we were just another species, pursuing our immediate survival needs without regard for long-term consequences. If we make that choice, we risk becoming not the inheritors of the Chicxulub legacy, but its newest casualties, another species that failed to adapt when the environment changed too quickly for evolution to keep up. The story of the day the dinosaurs died is ultimately a story about choice, change, and consequence. It shows us that even the most successful species, even the most stable ecosystems, can disappear when faced with forces beyond their ability to adapt. But it also shows us that life itself is incredibly resilient, creative, and persistent. Given enough time and opportunity, evolution will find ways to fill every available niche, to adapt to every challenge, to recover from every catastrophe. The question for our species is whether we will be part of that recovery or part of the catastrophe that makes recovery necessary. The asteroid that ended the Cretaceous period made that choice for the dinosaurs, but we have the unprecedented luxury of being able to make our own choices about the future of life on Earth. The cosmic bullet that struck our planet 66 million years ago didn't just end one chapter of Earth's story. It began writing an entirely new book, one whose pages are still being filled today. We are both the authors and the characters in that ongoing story, with the power to influence how it unfolds and what its ultimate meaning will be. Every choice we make about how we treat our planet, how we interact with other species, and how we use the remarkable capabilities that evolution has given us becomes part of that larger narrative. We are writing the next chapter of the story that began with the impact that killed the dinosaurs, and the ending hasn't been determined yet. The day the dinosaurs died was the day our story began. What we do with that beginning is up to us. The scientific revolution that followed our understanding of Chicxulub changed more than just paleontology. It fundamentally altered how we think about catastrophe itself. Before the impact theory gained acceptance, most scientists believed that major changes in Earth's history happened gradually over millions of years. Mountains rose slowly, climates shifted imperceptibly, species evolved at a measured pace that human minds could barely comprehend. The discovery of the iridium layer shattered this comfortable worldview. It showed that Earth's history wasn't just a story of slow, steady change, punctuated by the occasional volcanic eruption or ice age. It was a story of sudden, violent interruptions that could rewrite the rules of existence in a matter of hours. This revelation forced scientists to reconsider other mysterious events in Earth's past. If an asteroid could cause mass extinction 66 million years ago, what about the even more devastating extinction that occurred 250 million years ago? What about the strange disappearances that mark the boundaries between other geological periods? As researchers began looking for evidence of additional impacts, they discovered that Earth's history is littered with cosmic collisions. The planet bears the scars of hundreds of asteroid and comet impacts, though most have been erased by the relentless forces of erosion, tectonics, and time. Each newly discovered crater tells a story of destruction and renewal, of catastrophe followed by evolutionary innovation. But the implications extend far beyond our own planet. As astronomers have developed more powerful telescopes and detection systems, they've realized that impacts aren't rare events in the cosmic neighborhood. They're part of the fundamental architecture of planetary systems. Every solid body in our solar system tells the same story through its scarred surface. The Moon, with its ancient craters preserved for billions of years, serves as a museum of cosmic violence. Mars shows evidence of impacts so massive they may have stripped away much of its atmosphere. Even the gas giants bear the marks of collisions, with Jupiter's Great Red Spot possibly being a centuries-old storm system triggered by a massive impact. This cosmic perspective reveals something profound about our place in the universe. We live on a planet that exists in what astronomers call a cosmic shooting gallery. Asteroids, comets, and other debris left over from the formation of our solar system continue to hurtle through space, following orbital paths that sometimes intersect with Earth's trajectory around the Sun. Most of these objects are small, burning up harmlessly in our atmosphere as meteors. But larger ones, like the object that created Chicxulub, are out there waiting. They follow predictable orbits governed by the same gravitational forces that keep planets in their paths around the Sun. The question isn't whether another large impact will occur, it's when. Statistical analysis of impact craters suggests that Earth experiences a civilization-ending impact roughly once every 100 million years. The last major impact was 66 million years ago, which means we're well into the statistical window for the next one. But statistics don't determine fate. The next major impact could happen tomorrow, or it might not occur for another 200 million years. This uncertainty has driven one of the most important scientific endeavors of our time, the systematic cataloging of potentially hazardous asteroids. Unlike the dinosaurs, we have the technology to see our cosmic executioners coming. Ground-based telescopes and space-based observatories continuously scan the sky, tracking the orbits of objects that might someday threaten our planet. The numbers are both reassuring and terrifying. Astronomers have identified over 90% of the kilometer-sized asteroids whose orbits bring them near Earth. None of these known objects pose a threat for at least the next century. But there are countless smaller objects that remain undetected, and even a relatively small asteroid could cause regional devastation if it struck a populated area. The 2013 meteor explosion over Chelyabinsk, Russia, provides a sobering example of our vulnerability. That object was only about 20 meters across, tiny by Chicxulub standards, but its atmospheric explosion damaged thousands of buildings and injured over 1,000 people. If a similar object struck directly over a major city, the casualties could number in the millions. Yet, even as we've developed the ability to detect these threats, we've also begun developing the technology to defend against them. For the first time in Earth's history, a species has evolved the capability to potentially prevent its own extinction from cosmic impacts. This represents a fundamental turning point in the relationship between life and the cosmos. The physics of asteroid deflection are surprisingly straightforward. A small change in an asteroid's velocity, applied years or decades before a predicted impact, can alter its trajectory enough to make it miss Earth entirely. The key is early detection and intervention. The earlier we spot a potential threat, the smaller the push needed to deflect it. Several deflection methods have been proposed and tested. The simplest involves sending a spacecraft to rendezvous with the asteroid and using the spacecraft's gravitational pull to gradually alter the object's orbit. This gravity tractor method works slowly, but requires no complex technology beyond what we've already mastered for interplanetary missions. More dramatic approaches involve kinetic impactors, spacecraft designed to slam into asteroids at high velocity and physically knock them off course. NASA's successful DART mission in 2022 demonstrated this concept by deliberately crashing a probe into the asteroid Dimorphos and measurably altering its orbit. For the largest potential threats, nuclear devices might be necessary, not to destroy the asteroid, which could create multiple smaller threats, but to vaporize material from its surface and create a rocket-like thrust that pushes it away from Earth. The technology exists, but the political and logistical challenges of deploying nuclear weapons in space remain formidable. These defensive capabilities represent more than just technological achievement. They mark the first time in the 4.5 billion year history of our planet that life has developed the ability to consciously influence its own cosmic destiny. We are no longer passive victims of celestial mechanics. We have become active participants in shaping the future of life on Earth. But this power comes with profound responsibility. The same intelligence and technology that allow us to track and deflect asteroids also give us the ability to understand our place in the larger story of evolution. We know that we are the products of past catastrophes, that our existence depends on the stability of complex ecosystems, that our actions have consequences that extend far beyond our immediate experience. The dinosaurs ruled Earth for over 160 million years before their cosmic encounter ended their reign. Humans have existed as a species for only about 300,000 years, and our technological civilization is less than 10,000 years old. In cosmic terms, we are barely more than an experimental prototype, a recent evolutionary innovation whose long-term viability remains unproven. Yet in this brief span of existence, we have developed capabilities that no previous species possessed. We can look backward through deep time and understand the forces that shaped us. We can look forward and anticipate challenges that our descendants might face. We can even look outward to other worlds and imagine possibilities for life beyond our own planet. This unprecedented combination of knowledge and capability places us at a unique crossroads in the history of life on Earth. We can choose to use our understanding of the past to build a more resilient future. We can choose to apply our technology to protecting the biosphere that created us. We can choose to become the first species to consciously guide its own evolutionary trajectory. Or we can choose to ignore these responsibilities, to continue living as if we were just another species pursuing short-term survival strategies without regard for long-term consequences. If we make that choice, we risk becoming not the beneficiaries of the Chicxulub impact, but its next victims, another species that failed to adapt when environmental conditions changed too rapidly. The asteroid that killed the dinosaurs teaches us that extinction isn't always gradual or predictable. Sometimes it comes from the sky without warning, reshaping the world in ways that no amount of evolutionary success can prepare for. But it also teaches us that life itself is remarkably resilient and creative, capable of recovering from even the most devastating catastrophes and evolving into forms more complex and beautiful than what came before. We stand at the intersection of these two truths: the fragility of individual species and the persistence of life itself. Our choices in the coming decades and centuries will determine which side of that equation defines our legacy. We can choose to be agents of preservation, protecting the biological heritage that billions of years of evolution have created. Or we can become agents of destruction, triggering the next great extinction event through our own actions and choices. The cosmic perspective that emerges from understanding the Chicxulub impact provides both humility and hope. It reminds us vast cosmic drama that we are small, temporary players in a began billions of years before our species existed and will continue long after we are gone. But it also shows us that even the smallest players can have profound effects on the trajectory of that drama. The mammals that survived the impact weren't the largest or most impressive creatures of their time. They were small, humble animals that happened to have the right combination of traits to survive when the world changed around them. From these modest survivors emerged all the diversity of mammalian life that characterizes our modern world, including the lineage that eventually gave rise to human consciousness. This evolutionary history suggests that survival and success in the long term don't depend on dominance or size, or even intelligence in the traditional sense. They depend on adaptability, resilience, and the ability to find new ways of living when old ways no longer work. These are qualities that our species possesses in abundance, if we choose to use them. The story of the Chicxulub impact is ultimately a story about transformation. It shows us that even the most catastrophic events can become opportunities for renewal and innovation. The destruction that ended the age of dinosaurs also opened the door to the age of mammals, creating the evolutionary pathway that led to our own existence. As we face the challenges of our own time, from climate change to biodiversity loss to the ever-present threat of future cosmic impacts, we can draw inspiration from this ancient story of survival and renewal. The Earth has endured worse catastrophes than anything we currently face and has always found ways to recover and flourish. But recovery requires survivors, and survival requires choices. The dinosaurs had no choice when their cosmic bullet arrived 66 million years ago. They could only endure what they couldn't prevent or escape. We have the luxury of choice, but only if we choose to use it wisely. The day the dinosaurs died was also the day our story began. What we do with that beginning, how we choose to continue the narrative that started with catastrophe and led to consciousness, will determine not just our own fate, but the future of life on Earth itself. The next chapter of this cosmic story is ours to write, and the pen is in our hands. The immediate geological aftermath of the Chicxulub impact created a crime scene so vast and complex that scientists are still deciphering its clues today. Within hours of the collision, processes began that would leave permanent scars in the Earth's crust, telling the story of those first terrible moments with precision that rivals any forensic investigation. The initial crater formation happened in stages, each one preserved in the rock record like frames from a slow-motion film of planetary destruction. When the asteroid first struck, it created what geologists call a transient cavity, a temporary wound in the Earth's crust that was simply too large for the planet's gravity to maintain. The crater walls, unstable under their own weight, began collapsing inward almost immediately. But something even more dramatic was happening at the center of the impact site. The incredible forces involved in the collision had compressed the bedrock beneath the crater to pressures exceeding anything found naturally on Earth's surface. When this compressed material suddenly rebounded, it shot upward like a liquid droplet frozen in time creating a central peak that rose several kilometers above the surrounding crater floor. This peak ring formation, visible today in gravity maps of the buried crater, tells us something crucial about the scale of the impact. Only the most massive collisions create these complex crater structures. The Chicxulub crater belongs to an elite group of impact sites that represent the upper limit of what solid planetary surfaces can endure without being completely destroyed. The rock samples extracted from this central peak reveal conditions so extreme they challenge our understanding of matter itself. Minerals that normally form deep within the Earth's mantle were created instantly at the surface. Quartz crystals were shocked into forms that exist nowhere else on our planet except at nuclear test sites. Even the carbon in the rocks was transformed, creating microscopic diamonds in quantities that speak to pressures beyond imagination. But perhaps the most haunting evidence comes from what scientists call the ejector blanket, the layer of material blasted out from the impact site and deposited across the surrounding landscape. This isn't just rock and debris. It's a mixture of vaporized asteroid, melted bedrock, and fragments of the living world that existed in those final moments before impact. Within this ejector layer, researchers have found spherules of glass that formed when molten rock was blasted high into the atmosphere and then cooled rapidly during its fall back to Earth. Some of these glass beads contain tiny bubbles of ancient atmosphere, preserving samples of the air that existed on that terrible day. Others show evidence of having been heated to temperatures exceeding those found on the surface of the Sun. The distribution of this ejector tells its own story of destruction. The thickest deposits are found closest to the crater, where the debris layer can be several meters deep. But traces of impact material have been found thousands of miles away, carried by atmospheric currents, and deposited as a thin film across continents. This global distribution proves that the impact affected the entire planet, not just the immediate region around Ground Zero. Chemical analysis of the ejector reveals the deadly cocktail that was released into Earth's atmosphere. The asteroid struck a region rich in sulfur-bearing minerals, primarily gypsum and anhydrite. When these rocks were vaporized by the impact, they released massive quantities of sulfur dioxide into the atmosphere, enough to alter global climate for decades or possibly centuries. The sulfur release alone would have been catastrophic. Computer models suggest that the impact released between 100 and 1,000 billion tons of sulfur compounds into the atmosphere. To put this in perspective, this is roughly equivalent to all the sulfur that would be released by burning every fossil fuel deposit on Earth simultaneously. The resulting acid rain would have had a pH approaching that of battery acid, falling in quantities that could strip leaves from trees and poison freshwater ecosystems across the planet. But sulfur wasn't the only toxic component released by the impact. The target rocks also contained significant amounts of carbon in the form of limestone and organic matter. When vaporized, this carbon was converted to carbon dioxide and carbon monoxide, adding to the atmospheric burden of greenhouse gases. The immediate warming effect of these gases may have briefly counteracted the cooling caused by impact debris, creating a complex climate signal that researchers are still trying to decipher. The impact also released enormous quantities of nitrogen oxides, formed when the tremendous heat of the collision caused atmospheric nitrogen and oxygen to combine in ways that don't normally occur in nature. These compounds not only contributed to acid rain, but also may have damaged the ozone layer, increasing the amount of harmful ultraviolet radiation reaching Earth's surface. Perhaps most insidiously, the impact may have released significant amounts of mercury into the environment. Recent analysis of sediments from the impact period shows mercury concentrations that are thousands of times higher than normal background levels. This mercury would have bioaccumulated in food webs, potentially contributing to the extinction of species that survived the immediate effects of the impact. The thermal effects of the returning ejector created conditions that were literally hellish. As trillions of tons of superheated debris re-entered the atmosphere around the globe, the air itself became a radiant heat source. Any organic material exposed to this thermal pulse would have ignited spontaneously. Forests that had never experienced fire burst into flames simultaneously across entire continents. The scale of these wildfires defies comprehension. Charcoal layers from this period have been found on every continent, indicating that the fires were truly global in scope. In some locations, the charcoal deposits are several centimeters thick, suggesting that entire forest ecosystems were reduced to ash in a matter of hours or days. Or the smoke and soot from these fires added another component to the atmospheric shroud that was already blocking sunlight from the impact debris. But the fires weren't just destructive. They also played a crucial role in the long-term recovery of terrestrial ecosystems. The massive quantities of ash they produced contained concentrated nutrients that would eventually fertilize the soils of the post-impact world. Some plant species, particularly those adapted to fire-prone environments, may have actually benefited from this global conflagration, finding themselves with unprecedented opportunities to colonize burned landscapes. The hydrological effects of the impact were equally dramatic. The collision occurred in a shallow sea, instantly vaporizing billions of tons of seawater and launching it high into the atmosphere. This water vapor, mixed with the other impact debris, contributed to the global shroud that blocked sunlight, but it also fundamentally altered precipitation patterns around the world. In some regions, the increased atmospheric moisture led to torrential rains that lasted for months or years. These rains weren't the gentle showers that nourish normal ecosystems. They were acidic deluges that could dissolve limestone bedrock and poison any water body they contacted. The combination of acid rain and massive runoff from burned landscapes created freshwater systems that were essentially uninhabitable for most forms of aquatic life. The impact also triggered massive tsunamis that reshaped coastlines around the Gulf of Mexico and Caribbean. These waves, some possibly exceeding 100 meters in height, carried marine sediments hundreds of kilometers inland, creating the jumbled fossil deposits that first alerted scientists to the catastrophic nature of the extinction event. But perhaps the most persistent effect of the impact was its influence on global ocean circulation. The addition of massive quantities of fresh water from vaporized seawater and subsequent acid rain may have disrupted the thermohaline circulation that drives ocean currents around the globe. This disruption could have persisted for centuries, fundamentally altering climate patterns and making recovery more difficult for marine ecosystems. The biological effects of these physical and chemical changes unfolded with brutal efficiency. The first casualties were the photosynthetic organisms that formed the base of terrestrial and marine food webs. On land, the combination of darkness, cold, acid rain, and toxic gases killed plants across entire continents. In the oceans, the microscopic plankton that had been producing oxygen and removing carbon dioxide from the atmosphere for hundreds of millions of years began dying en masse. The collapse of photosynthesis had cascading effects throughout Earth's ecosystems. Not only did it eliminate the primary source of food for herbivorous animals, but it also disrupted the planet's oxygen and carbon cycles in ways that would persist for thousands of years. Atmospheric oxygen levels, which had been maintained by photosynthetic organisms, began to decline. Carbon dioxide levels, no longer being absorbed by plants and plankton, started to rise. These atmospheric changes created additional challenges for surviving organisms. Animals that had evolved in oxygen-rich environments found themselves struggling to breathe in air that was becoming increasingly depleted of the gas they needed to survive. The rising carbon dioxide levels also made the air more acidic, creating respiratory stress for many species. The few organisms that survived these initial effects faced a world that had been fundamentally transformed. The stable climate that had characterized much of the Cretaceous period was replaced by extreme variability. Temperatures swung wildly as different atmospheric components dominated at different times. Precipitation patterns became unpredictable, with some regions experiencing devastating droughts, while others were flooded by acid rain. Food webs that had been stable for millions of years collapsed and reformed in entirely new configurations. Herbivores that had once fed on abundant plant life found themselves competing for scattered remnants of vegetation. Carnivores faced starvation as their prey populations crashed. Even scavengers, which might have been expected to thrive in a world full of dead animals, struggled because the carcasses they depended on were often contaminated with toxic compounds from the impact. The psychological stress on surviving animals would have been enormous. Creatures that had evolved behavioral patterns based on predictable daily and seasonal cycles suddenly found themselves in a world where normal environmental cues had disappeared. The day-night cycle became meaningless in a world shrouded by impact debris. Seasonal changes, which had driven migration and breeding patterns for millions of years, were obscured by the overriding effects of impact winter. Many species probably survived the immediate effects of the impact, only to succumb to the chronic stress of living in a world that no longer made biological sense to them. Animals that had once navigated by celestial cues found themselves lost in perpetual twilight. Species that had timed their reproduction to seasonal changes found themselves breeding at inappropriate times, leading to reproductive failure and population collapse. But even in this global catastrophe, some organisms found ways not just to survive, but to exploit the new conditions. Decomposer organisms, particularly fungi and bacteria, suddenly found themselves in a world rich with dead organic matter. While other organisms starved, these decomposers began breaking down the massive quantities of dead plant and animal material, recycling nutrients, and preparing the ground for eventual ecosystem recovery. Some scavenging animals also found opportunities in the post-impact world. Species that had previously been minor players in Cretaceous ecosystems suddenly found themselves with access to resources that had been monopolized by dominant species. Small mammals that had spent millions of years hiding from dinosaur predators could now venture into territories that had been off-limits. The aquatic survivors faced their own unique challenges and opportunities. Freshwater ecosystems, while devastated by acid rain, recovered more quickly than marine environments because they were continuously flushed by new water from precipitation and runoff. Some freshwater fish and amphibians found that their tolerance for acidic conditions, evolved in response to natural environmental variation, gave them an advantage in the post-impact world. Marine ecosystems took much longer to recover, but when they did, they were fundamentally different from what had existed before. The great marine reptiles that had dominated Cretaceous seas were gone forever, but their absence created opportunities for other groups to diversify and expand. Some fish lineages began exploring ecological roles that had previously been occupied by reptiles. Early marine mammals began the evolutionary journey that would eventually lead to whales and dolphins. The recovery process wasn't uniform across the planet, or even within individual regions. Some areas that had been hit particularly hard by the immediate effects of the impact remained barren for hundreds of thousands of years. Others, especially those with abundant freshwater sources and some protection from the worst of the environmental damage, began showing signs of biological recovery within decades of the impact. This variability in recovery patterns created a patchwork of different evolutionary experiments across the post-impact world. In regions where recovery was rapid, intense competition between surviving species drove rapid evolutionary change. In areas where recovery was slow, the few surviving species had opportunities to diversify into multiple ecological roles without facing competition from established communities. The fossil record from this period reveals fascinating insights into how evolution responds to sudden environmental change and ecological opportunity. Some surviving mammal lineages began diversifying almost immediately after the extinction, evolving into new body sizes and ecological roles within just a few 100,000 years. Others remained conservative, maintaining the small body sizes and generalized diets that had allowed them to survive the extinction in the first place. Plant evolution also accelerated in the post-impact world. Flowering plants, which had been present but not dominant during the Cretaceous, began diversifying rapidly in the aftermath of the extinction. Some evolved new strategies for surviving in disturbed soils and variable climates. Others developed new relationships with animal pollinators and seed dispersers, creating the complex plant-animal partnerships that characterize modern ecosystems. The speed of these evolutionary changes challenges traditional ideas about the pace of biological innovation. Before the discovery of the Chicxulub impact, most scientists believed that major evolutionary transitions required millions of years to unfold. The post-impact fossil record shows that significant evolutionary change can occur in hundreds of thousands of years when environmental pressures are severe and ecological opportunities are abundant. This rapid pace of evolution was driven partly by the empty ecological space left by the extinction, but also by the new types of environmental challenges that survivors faced. The post-impact world was more variable and unpredictable than the stable greenhouse conditions that had characterized much of the Cretaceous. This environmental instability favored organisms that could adapt quickly to changing conditions. The genetic mechanisms that enabled this rapid evolution are still being studied, but they likely involve changes in gene expression patterns rather than entirely new mutations. Many of the traits that proved advantageous in the post-impact world, such as behavioral flexibility and physi-environmental variation, virological tolerance were probably present in small amounts in pre-extinction populations, but became strongly favored after the environmental changes caused by the impact. This process of rapid evolutionary change, driven by environmental catastrophe, has important implications for understanding how life might respond to current environmental changes. The same mechanisms that allowed some species to survive and diversify after the Chicxulub impact may be operating today as ecosystems respond to human-induced environmental pressures. The parallels between the post-Chicxulub world and our current environmental situation are both encouraging and sobering. They suggest that life is remarkably resilient and capable of recovering from even the most severe environmental catastrophes. But they also show that recovery takes time, often much longer than human timescales, and that what emerges from environmental catastrophe is rarely the same as what existed before. The story of recovery from the Chicxulub impact is ultimately a story about the creative power of destruction. The asteroid that ended the Cretaceous period didn't just kill the dinosaurs and clear the way for mammals. It fundamentally reset the evolutionary game, creating new rules and new opportunities that led to forms of life that had never existed before. This creative aspect of mass extinction reveals something profound about the nature of evolution itself. Evolution isn't just about gradual improvement and increasing complexity. It's also about radical experimentation, about trying entirely new approaches to the challenges of survival and reproduction. Mass extinctions accelerate this experimental process by removing the established species that might otherwise prevent new innovations from gaining a foothold. The Chicxulub impact was the ultimate evolutionary experiment, one that tested every assumption about how life on Earth could be organized. The results of that experiment are still unfolding today, in the ecosystems that surround us, in the species that inhabit our planet, and in our own existence as conscious beings capable of understanding our place in this vast cosmic story. Understanding this story changes how we see ourselves and our relationship to the natural world. We are not separate from the evolutionary process that shaped life on Earth. We are products of that process, carrying within our genes and our consciousness the legacy of every organism that survived the Great Extinction 66 million years ago. The asteroid that killed the dinosaurs is in our neural pathways, written into our DNA, encoded in the very structure of our thoughts and dreams. This knowledge brings both humility and responsibility. It reminds us that our existence is contingent, dependent on a chain of events so unlikely that it borders on the miraculous. But it also shows us that we are part of something larger than ourselves, participants in an ongoing story of survival, adaptation, and renewal that connects us to every other living thing on our planet. The day the dinosaurs died was not the end of their story. It was the beginning of ours. And the story continues to unfold with every choice we make, every action we take, every decision we face about how to use the remarkable gifts that evolution has given us. The asteroid that fell from the sky 66 million years ago is still falling, still shaping our world, still reminding us that we are all children of catastrophe, heirs to destruction, and architects of whatever comes next. The story doesn't end with recovery. It continues with a revelation that changes everything we thought we knew about life's relationship with destruction. Because while scientists were piecing together the immediate aftermath of Chicxulub, they discovered something that defied every assumption about mass extinction. The impact didn't just randomly eliminate species based on size or strength or evolutionary sophistication. It operated according to rules so precise, so specific, that they read almost like a cosmic algorithm for determining survival. The pattern emerged slowly, hidden within thousands of fossil specimens collected from sites around the world. At first, it seemed random. Some small animals died while others lived. Some large animals perished while a few survived. But as researchers compiled more data, analyzed more specimens, and compared survival rates across different groups, a startling truth began to emerge. The asteroid hadn't of selection, operating of destruction. It had been a force at just been a force according to criteria that evolution itself seemed to have written into the fabric of life. Animals that survived the impact shared certain characteristics that had nothing to do with their size, their intelligence, or their position in Cretaceous food webs. Instead, they shared traits that would prove crucial for surviving in a world turned upside down. Consider the puzzle of why birds survived while pterosaurs didn't. Both groups were capable of flight. Both had hollow bones and efficient respiratory systems. Both could potentially escape the immediate effects of ground-based catastrophes by taking to the air. Yet every single pterosaur species vanished while several bird lineages made it through the extinction bottleneck. The answer lies not in their similarities, but in their differences. Birds that survived the impact were generally small-bodied species with relatively simple dietary requirements. Many were seed-eaters, capable of surviving on the dormant seeds that remained viable in post-impact soils long after the plants that produced them had died. Others were insectivores that could exploit the abundant dead organic matter and the decomposer organisms that thrived on it. Pterosaurs, by contrast, were often large-bodied animals with specialized diets. Many were fish-eaters that depended on healthy marine ecosystems. Others were fruit specialists that required flowering plants to survive. When the environmental foundation that supported these specialized lifestyles collapsed, the pterosaurs had nowhere to turn. Their very success in exploiting specific ecological niches became their downfall when those niches disappeared. This pattern repeated itself across every major group of organisms. Among mammals, the survivors weren't the largest or most advanced species. They were small, generalized forms that could eat almost anything and reproduce quickly when conditions allowed. Among reptiles, the survivors were often burrowing species that could retreat underground when surface conditions became uninhabitable. Among plants, the survivors were frequently those with hardy seeds that could remain dormant through adverse conditions. But the selection criteria went even deeper than diet and behavior. The impact seemed to favor organisms with what biologists call phenotypic plasticity, the ability to change their characteristics in response to environmental conditions. This wasn't genetic evolution happening between generations. This was individuals modifying their physiology, behavior, or even anatomy during their own lifetimes to cope with changing circumstances. This type of flexibility was virtually unknown among the highly specialized creatures that dominated Cretaceous ecosystems. Dinosaurs, for all their evolutionary success, were generally locked into specific ecological roles by their anatomy and behavior. A triceratops couldn't suddenly become a carnivore if plant food became scarce. A Tyrannosaurus couldn't switch to eating seeds if large prey animals disappeared. The organisms that survived were those that could switch. Small mammals could alter their diets, their activity patterns, their reproductive timing. Birds could change their foraging strategies, their migration routes, their nesting behaviors. Plants could modify their growth patterns, their chemical defenses, their reproductive strategies. This behavioral and physiological flexibility became the ultimate survival trait in a world where the rules of existence were being rewritten daily. The implications of this discovery extend far beyond paleontology. They reveal something fundamental about the relationship between specialization and vulnerability in biological systems. In stable environments, specialization is often advantageous. Organisms that can exploit specific resources more efficiently than their competitors will generally outcompete more generalized forms. But when environments change rapidly, specialization becomes a trap. The more precisely an organism is adapted to specific conditions, the more vulnerable it becomes when those conditions disappear. The Chicxulub impact was the ultimate test of this principle, creating environmental changes so severe and so rapid that only the most flexible organisms could survive. This understanding has profound implications for how we think about current environmental changes. As human activities alter ecosystems around the world, we may be creating selection pressures similar to those that operated during the mass extinction. Species that are highly specialized for current conditions may be the most vulnerable to future changes, while those that retain flexibility and adaptability may be the most likely to survive. The fossil record from the extinction boundary also reveals another surprising pattern. Many of the organisms that survived the immediate crisis didn't just persist, they thrived in ways that would have been impossible in the pre-impact world. The environmental catastrophe that eliminated so many species also removed the competitive pressures that had previously prevented survivors from expanding into new ecological roles. Small mammals that had spent millions of years hiding in burrows suddenly found themselves free to explore surface environments that had been dominated by dinosaurs. Birds that had been restricted to specific dietary niches discovered that the collapse of established food webs created opportunities to experiment with entirely new feeding strategies. Even plants found that the death of established forest communities opened up growing space that had been monopolized by dominant species for millions of years. This pattern of post-extinction opportunity reveals something crucial about the relationship between destruction and innovation in evolutionary systems. Mass extinctions don't just remove species randomly. They preferentially eliminate the dominant specialized forms that have been most successful under previous conditions. This creates what ecologists call ecological release, a situation where surviving organisms suddenly find themselves free from the competitive constraints that had previously limited their evolutionary options. The result is often an explosion of evolutionary innovation as survivors diversify rapidly to fill empty ecological niches. This process, called adaptive radiation, is responsible for some of the most dramatic examples of evolutionary change in Earth's history. The mammalian radiation that followed the Chicxulub impact was one of the most spectacular examples, producing everything from tiny shrews to enormous whales within just a few million years. But the speed and creativity of post-extinction evolution also depends on the genetic and developmental flexibility of surviving organisms. Species that survive mass extinctions often possess what biologists call evolutionary potential, hidden genetic variation that can be expressed when environmental conditions change. This variation may be invisible under normal conditions, but becomes crucial when organisms face new challenges or opportunities. The mammals that inherited the post-Chicxulub world carried within their genes the blueprints for an astonishing variety of body plans and lifestyles. Within just a few million years of the extinction, mammalian lineages had evolved forms adapted for running, swimming, flying, digging, climbing, and every other conceivable mode of life. This rapid diversification wasn't the result of sudden genetic mutations. It was the expression of genetic potential that had been accumulating over millions of years of mammalian evolution. This genetic flexibility may explain why certain groups of organisms seem to be particularly successful at surviving mass extinctions and diversifying afterward. Mammals, birds, flowering plants, and certain groups of marine organisms have all survived multiple extinction events and radiated extensively in their aftermath. These groups may share certain genetic or developmental characteristics that make them particularly good at evolving rapidly when opportunities arise. Understanding these patterns has important implications for conservation biology and our efforts to protect biodiversity in the face of current environmental changes. If we can identify which species possess the greatest evolutionary potential, we may be able to focus conservation efforts on preserving the organisms most likely to survive and adapt to future changes. The study of mass extinctions also reveals the importance of what scientists call refugia, small areas where organisms can survive environmental catastrophes that devastate the surrounding landscape. During the Chicxulub impact, certain geographic regions experienced less severe environmental effects than others. These refugia became the seed banks from which post-extinction ecosystems eventually grew. Modern conservation efforts often focus on creating protected areas that could serve similar functions during future environmental crises. By preserving habitat diversity across different geographic regions and elevations, we may be able to ensure that some populations of important species survive, even if their main populations are eliminated by environmental changes. But perhaps the most important lesson from the Chicxulub extinction concerns the role of chance in determining survival and extinction. While certain traits like small body size and dietary flexibility improved survival odds, they didn't guarantee survival. Many small, flexible organisms died, while some large, specialized ones survived. The boundary between life and death was often determined by factors as random as geographic location at the time of impact or access to local refugia. This element of chance reveals something humbling about our own position in the ongoing story of life on Earth. Our survival as a species isn't guaranteed by our intelligence, our technology, or our apparent dominance over other organisms. Like every other species that has ever lived, we remain vulnerable to environmental changes that could overwhelm our adaptive capabilities. Yet the story of the Chicxulub impact also provides hope. It shows that life is remarkably resilient and creative, capable of recovering from even the most devastating catastrophes and evolving into forms more complex and beautiful than what came before. The mammals that inherited the post-impact world weren't just successful survivors. They became the architects of ecosystems more diverse and intricate than anything that had existed during the age of dinosaurs. The flowering plants that expanded after the extinction didn't just replace the ferns and conifers that had dominated before. They created entirely new types of ecological relationships, forming partnerships with pollinators and seed dispersers that added layers of complexity to terrestrial ecosystems. The marine organisms that survived in the oceans didn't just refill empty niches, they invented new ways of living in aquatic environments. This creativity in the face of catastrophe suggests that evolution itself may be fundamentally opportunistic, always ready to experiment with new possibilities when environmental changes create space for innovation. Mass extinctions, while devastating in the short term, may actually accelerate the long-term creative potential of evolutionary systems by removing the dominant forms that might otherwise prevent experimentation with new approaches to survival. The Chicxulub impact represents the ultimate example of this creative destruction. The asteroid that seemed to bring only death and darkness to the Cretaceous world actually opened evolutionary pathways that had been closed for over 160 million years. The mammals, birds, and flowering plants that diversified in its aftermath didn't just replace what had been lost, They created biological innovations that had never existed before. Understanding this pattern changes how we think about our own relationship with environmental change and uncertainty. Instead of viewing environmental challenges as purely destructive forces that threaten our survival, we can begin to see them as potential catalysts for innovation and adaptation. The key is maintaining the flexibility and creativity that have allowed life to survive and thrive through billions of years of planetary changes. The cosmic perspective that emerges from studying the Chicxulub impact reminds us that we live on a dynamic planet in a universe filled with both creative and destructive forces. The same processes that made our existence possible continue to operate today, reshaping our world in ways we can barely imagine. Our challenge is to learn how to work with these forces rather than against them, using our intelligence and technology to enhance rather than diminish the creative potential of the evolutionary process. The day the dinosaurs died wasn't just an ending, it was a beginning, a moment when the universe demonstrated its capacity for both destruction and renewal on a planetary scale. The story that began with that terrible impact continues to unfold today in every ecosystem that surrounds us, in every species that shares our planet, and in our own ongoing evolution as conscious beings, capable of understanding and perhaps even guiding the forces that shaped us. We are the products of that ancient catastrophe, the inheritors of the world it created, and the authors of whatever comes next in this cosmic story of survival, adaptation, and endless becoming. The story we've traced today stretches across 66 million years, from a moment of cosmic violence to the world we inhabit now. Every forest you've walked through, every bird you've watched take flight, every breath you've drawn exists because of what happened on that terrible day when the sky caught fire and the earth trembled beneath the weight of destruction. We are not separate observers of this ancient catastrophe. We are its living legacy, carrying within our very cells the genetic memory of creatures that crawled through ash and darkness, that found ways to endure when everything familiar had vanished. The Chicxulub impact didn't just reshape continents and climate. It rewrote the fundamental rules of what life could become. Yet perhaps the most remarkable truth hidden within this story is that we now possess something no previous inhabitants of Earth ever had. The power to see our cosmic threats approaching, the technology to potentially deflect them, the wisdom to understand that we are both fragile and resilient, temporary and eternal, products of chance and architects of choice. The asteroid that killed the dinosaurs reminds us that our planet exists in a universe both creative and destructive, where endings become beginnings and catastrophe becomes opportunity. As we face our own uncertain future, we carry with us the deepest lesson of that ancient day. Life doesn't just survive. It transforms, adapts, and finds ways to write new chapters even from the ashes of the old. The dinosaurs had their day. Now we have ours. What we choose to do with it will echo through deep time, just as that cosmic impact still echoes in every living thing around us. The story continues, and we get to help write what happens next.